Hi everyone, welcome to Lattice Semiconductor Developers Conference 2024 breakout session. In this breakout session, we will focus on tools and techniques for higher design efficiency. My name is Sukrut Kumar Krishnamurthy and I will be your presenter for this session. I work as a staff application engineer at Lattice Semiconductor, specializing in FPGA software tools. I also provide customer support as a tools and timing expert. I have over 10 years of semiconductor industry experience and a master's degree in electrical engineering from San Jose State University. I'm also a key contributor to Lattice's internal and external training contents for software tools. Today in this session, let's look at some of the advantages of using Radiant feature tools in the design process. Feature tools such as Virtual I/O flow, block-based design flow, isolation design flow, incremental design flow, which are supported in Radiant software, and finally conclude with some frequently asked questions. Now let's look at some of the benefits of using Radiant feature tools in the design process. The Virtual I/O flow in Radiant software is designed to help when your design needs more I/O pins than that are available on the device. It's specifically useful for developing IP modules. Virtual I/O flow offers enhanced flexibility where you can design without being constrained by external I/O mapping, making it easier to iterate and innovate. It also helps in performance and estimation, helping you optimize your IP before even committing to hardware. Another feature tool in Radiant is a block-based design flow. This block-based design flow offers a quick solution to timing closure by helping lock critical device performance. It also helps in reusing some of the blocks, which saves time across projects. Another crucial feature that Radiant supports is an isolation design flow. This isolation design flow helps integrate safety critical blocks using the exclusive macro option and allows controlled access to only approved signals to access the macros. Finally, we have an incremental design flow, which is currently in the beta stage, which provides help in performance preservation and helps achieve predictable results. Now let's look at each of these feature tools that are available in Radiant in a much more detailed depth. The first feature that we will look at is the Virtual I/O flow. Are you looking to assess the performance or resource usage of a module or IP, but often find yourself constrained by the availability of the I/O resources? When you use this, do you also get an error saying design doesn't fit into device specified? Refer to the map report for more details. Then your answer to this is the Virtual I/O flow. Now let's dive into the Virtual I/O flow. This Virtual I/O flow feature is designed to help when your design needs more I/O pins than that are available on the device. It's especially useful for developing IP modules. Here's a breakdown of what this feature offers. Mapping and place and route completion. Even if your design requires more I/O pins than the device has, you can still complete the mapping and place and route processes. This means you can keep working on your design without being stopped by the I/O limitations. Instead of being connected to a physical pin, a virtual I/O will be terminated in a lookup table, thus allowing you to complete the map and place and route process. This process is very useful for IP development. This feature is great for IP development because it allows you to accurately evaluate the performance and resource utilization of your IP modules, even when the physical I/O resources are limited. This setup allows for accurate evaluation of IP resources and performance, ensuring that you can test and optimize your design effectively. Another benefit of using Virtual I/O flow is that it provides easy constraining. You can easily apply design constraints to your design using the device constraint editor or the physical design constraints files using Radiant. This helps in managing the virtual IOs more effectively. You can use the LDC underscore set underscore attribute constraint with the virtual IO attribute to manage the virtual IOs. This also supports the use of wildcards on port names, making it easier to apply constraints to multiple ports at once. Please note, while you're using the virtual IO flow, bitstream generation will be disabled. If you attempt to generate a bitstream for a design with virtual IO, you will encounter an error as the bitstream generation is not supported in this scenario. Now let's talk about the virtual IO usage guidelines. First off, let's talk about adding virtual IO constraints. You can add these constraints to your .pdc file, which is your physical design constraints files. This is where you define how your design would be implemented on the hardware. When it comes to the syntax for setting a port as a virtual IO, you can use a command like ldc underscore set underscore attribute, virtual IO equal to true, get underscore ports, and specify the port name. A cool thing here is that you can also use wildcards on port names, which makes it easier to apply design constraints to multiple ports at once. For example, if you want to set all ports that starts with data underscore in as virtual IOs, you would write something like ldc underscore set underscore attribute, virtual IO equal to true, get ports, data in, and a star in the square brackets. You can also use the Design Constraint Editor or DCE to edit the attributes for virtual IOs. The DCE has a virtual column where you can specify a port as virtual, making it straightforward to manage these settings. Next, the map report is really handy because it provides details on the resource usage for your virtual IOs. This report will help you understand how much of the device's resources are being used by the virtual IOs. Additionally, the map PIO attribute tables also lists these virtual IOs so you can keep a track of them easily. For accurate resource estimation, it's important to subtract the feed-through LUTs from the total number of LUTs to give you a clear picture on the actual resources being used by your design. Lastly, keep in mind that the virtual IOs are not listed in the signal or pad report, which is a part of the place and route reports. This means you won't see them in that particular report, so you'll need to rely on the map report and the PIO attribute table for information on the virtual IOs. When using the virtual IO flow, there are some important considerations to keep in mind. This flow is generally supported, but there are specific cases where it might not be applicable. Here are the key points. Unsupported cases. Tri-state signals. If an IO port is associated with a tri-state signal, virtual IO flow is not supported. A location constraint. If an IO port already has a location constraint, it cannot be used as a virtual IO. The IO type attribute. If the IO port has an IO type attribute defined in the user RTL or constraint, then the virtual IO flow is not supported. A delay module. If the IO port is connected to the delay module, it cannot be used as a virtual IO. Special IO buffers. Ports that are not simple input-output buffers, such as MIPI or SEIO Core 18, are not supported for virtual IOs. Clock signals. If the IO port drives a clock signal or is driven by a clock signal, it cannot be used as a virtual IO. Direct external IO connection. If the IO port is directly connected to an external hardware, such as APIO pins, JTAG ports, IDDR's D input, ODDR's Q output, or a DQS input, the virtual IO flow is not supported. This flowchart gives you a flow where virtual IO flow is used in the Radiant design process. During pre-synthesis or post-synthesis, you can specify virtual IO ports in the constraint files and RTL files. In the map process will include the virtual IO constraints. The place and route process will also consider these constraints. However, please note that as stated before, bitstream generation will be disabled when virtual IOs are inserted in the design. You can always use the back annotation to refine the design after place and route. In summary, while the virtual IO flow is a powerful tool, it has some limitations and specific cases where it cannot be applied. It's important to be aware of these exceptions to ensure a smooth design process. Moving on, let's now look at another feature tool supported in Radiant for higher design tools and efficiency: the block-based design flow. The block-based design flow, also known as the macro design flow in Radiant software, offers several key benefits that significantly enhances the design process for complex projects. This methodology is particularly advantageous for managing large-scale designs and improving overall productivity. Block-based design provides a faster timing closure. This approach helps in locking down critical blocks early in the design process, which reduces the timing closure issues. By focusing on the critical blocks, the overall project completion time is sped up, leading to increased productivity. Block-based design flow offers a design reuse across projects. One of the major advantages is the ability to reuse design blocks across different projects. This minimizes the effort required, cuts costs, and accelerates the time to market. It extends the design reuse beyond just the RTL level, providing substantial productivity benefits. Block-based design also provides an enhanced team-based design. This block-based design flow improves collaboration and efficiency in team environments by fostering a better teamwork. It contributes to the overall success of the project. Now let me introduce the concept of macros. What are macros? Macros are sub-blocks within a design that are preserved and intended for reuse. They are essentially smaller components of a larger design that can be reused across different projects or parts of a project. The reason for preservation. The reason for preserving these macros varies, but the main intention is that they are parts of the design that do not change often. This stability makes them reliable and efficient for reuse. Each macro preserves a different amount of information about itself depending on its level of preservation. This means that some macros might retain more detailed information than others based on how critical they are to the design. Some of the potential benefits of reusing macros are design reuse. In this case, macros allows for the reuse of design components, which can save time and effort in the design process. By reusing the sub-blocks, designers can avoid duplicating work and focus on the new aspects of the design. Another benefit of using the macros is that it ensures timing closure within critical blocks. By preserving critical blocks such as macros, designers can ensure that these parts of the design meet their timing requirements. This helps in achieving timing closure more efficiently. Another benefit of using macros is that it isolates portions of the design flow for functional safety. Macros can be used to isolate certain parts of the design flow, which is important for functional safety. This isolation ensures that the changes in one part of the design do not affect other critical areas. Another potential benefit of using the macro is that it stabilizes the Fmax of a macro. By ensuring that a macro does not change between compilations, its maximum operating frequency, or an Fmax, can be stabilized. This consistency is crucial for maintaining the performance of the design. And finally, macros help in team-based design. Macros facilitate team-based design by allowing different team members to work on separate sub-blocks. This modular approach improves collaboration and efficiency within the team. In summary, macros are preserved sub-blocks within a design that offers several benefits, including design reuse, timing closure, functional safety, performance stability, and enhanced team collaboration. These advantages make macros a valuable tool in the design process. Now let's look at the type of macros. There are three main types of macros used in the design process. The first one is the logical macro. The logical macro contains information from the netlist after synthesis. These macros are defined before synthesis using a macro creation constraint. The resultant macro is generated after the synthesis process, which contains the post-synthesis netlist information. The second type of macro is the firm macro. The firm macros contain placement information from the design after the map and par process. These macros are defined after synthesis and map using a macro region constraint or by using the physical designer in Radiant. The resultant macro is generated after the place and route process. The hard macro is the third type of macro. The hard macros contains placement and routing information from the design after the place and route process. These macros are defined after synthesis using a macro region constraint or by using the physical designer. The resultant macro is generated after the par process. In summary, the type of macros, logical, firm, and hard, differ based on the stage of the design process they are defined and the type of information they contain. Logical macros are defined pre-synthesis, firm macros are defined during place and route, and hard macros are post-synthesis but pre-place and route. Each type of macro serves a specific purpose in preserving and reusing design information at different stages of the design flow. Here's a step-by-step guide on how to create macros. The first step is to define the initial macro. The initial macro can be defined using the pre-synthesis timing constraint editor by navigating to the macro tab. Once you are here in the timing constraint editor, add the LDC create macro command to the active pre-synthesis constraint file. The second step is to run synthesis. In this stage, you will execute the synthesis process to generate the initial macro. The third stage is an optional stage where you define the macro region. This is used only if you are trying to create a firm and a hard macro. This can be done using the physical designer by creating a macro region if needed. You can also add constraints such as LDC create region and LDC set location constraint to the active post-synthesis constraint file manually. The fourth step is to run map and par process. In this stage, you will execute the map and the place and route process to finalize the macro. Once place and route is completed, the fifth step would be to export macro or generate the bit stream. After completing the map and par process, you can either export the macro or generate the bit stream. In summary, creating macro involves defining the initial macro, running synthesis, optionally defining a macro region, running the map and par process, and finally exporting the macro or generating the bit stream. This flow ensures that the macro is properly integrated and ready to use in your design. This slide provides details on the constraints used for defining logical and physical macros. Logical macros. You can use the command ldc_create_macro, -name and specify the macro name, -use PIO, a comma separated port names, and get cells -hierarchical and the macro instance name. This command is used to create a logical macro. You need to specify the macro name, the ports to be used, and the hierarchical instance name of the macro. Second, if you want to create a physical macro, you have to start by creating a macro region. This macro region can be created using the physical designer tool. You can also add the command ldc_create_region, -name, macro region name, -site, anchor for the macro region, -width, specifying the width, -height, -buffer left, a buffer right, buffer top, buffer bottom option. This command is used to create a macro region. In this command, you need to specify the region name, the anchor site for the region, and the dimensions such as height and width, along with the buffer sizes for creating a macro. Once this is done, you will also have to set the location by adding the LDC underscore set underscore location constraint. This command is used to set the location of a logical macro within a specified macro region. You need to specify the region name and the logical macro name. After a macro is generated, it can be exported for reuse in other designs. Here's how the process works. As we mentioned that there are three types of macros: a logical macro, a firm macro, and a hard macro. A logical macro contains post-synthesis netlist information. A firm macro contains a generated post-map and placement information, and a hard macro contains a generated post-bar information, including routing. And the preservation level of an exported macro can be lowered once the macro is added to a design. Exporting as a hard macro allows you to choose whether to implement it as a hard, firm, or a logic macro later on, depending on your needs. If you want to export a macro, you need to go to the tools and select export macros. Here, you need to choose the macro that you want to export. You should also decide on the preservation level for the macros, and you need to set the general settings for the macro. And finally, you need to export the macro. All the information regarding the macro and creating and exporting macros can be found using the Radiant help document. Previously, we discussed how to export macros for reuse in other designs. Now let's move on to show you how you can reuse these exported macros in your project. To reuse a macro, you need to follow these steps. Add the existing macro file. You can go to the files, add existing file into your design software, instantiate the macro in your design by providing the macro module name, and you can also optionally modify the level of preservation. By default, reuse macros are set to their highest level of preservation. To change this, you can always right-click and unselect Properties. Under the Preservation Level drop-down menu, you can select a lower level of preservation if needed. Note that you can also set it to lower level than it was originally exported with. When you're adding a macro, you can set a file type to the input files, such as a .vhtl file, a .v file, to ensure the correct format is selected. You can add the exported macro from the implementation directory. By default, exported macros are saved in the current project's implementation directory. In summary, reusing macros involves adding the existing macro file to your project, optionally modifying the preservation level, and ensuring the correct file type is selected. This process allows you to efficiently integrate previously defined macros and into your new designs, enhancing productivity and consistency. Continuing from our previous discussions on reusing macros, let's now look at some of the important guidelines for creating and managing macros effectively. Creating macros. Macros cannot share the same name as its source instances. All type of macros requires an instance name. Macros cannot be at the top level file in a project. It must be used as a wrapper to instantiate submacro blocks. Macros cannot contain shareable device hard IP such as JTAG-H, PCS, etc. A macro cannot contain black boxes or other macros inside them. You need to ensure that the macro region has sufficient resources for the physical macros being created. Some of the things to keep in mind for exporting and reusing macros. The timing model of macros is not supported for reuse, which means synthesis cannot optimize the macro I/O data paths based on the macro contents. Multiple instances of the same physical macro cannot be instantiated in a design. Users have to ensure that the target device has sufficient resources for all macros in the design if there are multiple macros. You need to make sure you always target the same device when reusing macros. Physical macros or hard macros are very strict due to this placement and routing information present in them. Hard macros cannot be moved during reuse. Switching gears, let's move on to another feature tool supported in Radiant, which is the isolation design flow as a continuation of the macro design flow. An isolation design flow is a method designed to enhance the security and integrity of FPGA designs by controlling signal access and isolating critical blocks of the design. The isolation design flow provides a secure integration where the content of the macro can only be accessed by the approved signals from the main design. This ensures that only the right signals can interact with these critical blocks, enhancing security. Isolation design flow also provides signal specification to the user. Designers can specify which signal interferes with the rest of the design that comes out of this isolation design. Clocks and resets are allowed to go from the main design into the secure region, maintaining necessary functionality. Placement and routing lock. The inner macro locks placement and routing information, thus preventing any other logic from using the empty or buffer region for placement or routing. This exclusion is key to maintaining the isolation and security of the critical design blocks. In summary, these guidelines emphasize the importance of controlling signal access, and isolating critical blocks to enhance the security and integrity of FPGA designs. By following these best practices, you can ensure that your designs are secure and reliable. Now let's delve into the process of creating and managing the isolation regions within your FPGA design. In the Physical Designer tool, you can right-click on the floor plan layout and select Create Isolation Region. Once you click on the Create Isolation Region, you can draw a rectangle around the sides for the isolation region. Physical Designer creates a prohibited region on each side, restricting access to the macro content. Now to create inner and outer macros, you need to lock the placement and routing, excluding the other logic. This is done by using the inner macro. The outer macro can be used as an empty macro, preventing any logic or routing inside. These steps are crucial for ensuring that your isolation regions are properly defined and managed, maintaining the integrity and security of your FPGA design. By following these guidelines, you can effectively isolate critical design blocks and control signal access, further enhancing the reliability of your designs. More information on creating and managing isolation regions can be found in Radiant Help document. Now let's look at another feature, incremental design flow. This incremental design flow is supported in the beta stage in the Radiant 2024.1 and 2024.2 release. The incremental design flow allows users to make incremental changes to the design to improve the overall design performance. This incremental design flow preserves specific process outcomes and performance within the portions of the design, thus minimizing the reprocessing time by concentrating on different parts of the design across multiple processing iterations. Some of the benefits of using incremental design flow is that it provides predictable results and performance changes during multiple iterations. Incremental design flow can reduce reprocessing runtime during multiple iterations. The incremental design flow is also supported by different synthesis tools and implementation processes for debug purposes. Now let's look at how the incremental design flow works. The incremental design flow requires a reference run. The incremental design flow compares the reference run with the incremental run to provide the desired results. As you can see in the images below, there has to be a reference run that includes synthesis, map, place and route, and bitstream generation. During the incremental run, users can do minimal changes to the RTL, And during synthesis, synthesis preserves most of the resources during synthesis process and only will work on the parts of the design that were changed. During map and par processes, again, map and par processes will reuse most of the resources during implementation and only will work on the parts of the design that were changed. The same thing happens with the bitstream generation. The bitstream generation only affects the changed bits in the bitstream. Thus, by using the entire incremental design flow, users can expect minimal runtime during incremental run. The incremental design flow works for synthesis and implementation processes. During synthesis, incremental synthesis uses compile points. These compile points are RTL partitions that can be user-defined or automatically generated by the synthesis tools. The synthesis tools then treat each compile points as a block and thus can synthesize, optimize, place and route the compile points independently. There are 4 types of compile points that are provided currently: a soft, hard, locked, and locked partition compile points. The details of each of these compile points can be found in the Synthesis or Simplify Pro user guide. Now let's see how to enable these compile points. Compile points can be enabled in 2 ways: automatic compile points or manual compile points. To enable an automatic compile point for Simplify Pro, in Radiant GUI Simplify Pro strategy settings, set the auto compile point to true. By default, this option is set to false. And also you need to set the resynthesize all option to false. By default, this option will be set to true for the rest of the designs. To enable a manual compile point, user has to define the manual compile points in Simplify Pro scope and save it to a .fdc file. Alternatively, users can also enter the following commands in the FDC file. Define _compile _point with the instance name and the type of the compile point. Manual compile points are only recommended for smaller designs, and you should always let the tool to define the auto compile points if your design is a large design. The beta version of the incremental synthesis or incremental design flow is supported through Simplify Pro. Now let's look at the compile point reports. When you're using Simplify Pro synthesis, Simplify Pro synthesis logs has a summary of compile points. Example of a reference run can be found in this image, in the first image. As you can see, in the summary of compile points lists the name of the instance, the status of the instance, and the reason for the change, and its start time and end time and a real time. In the next section here, we talk about the example report of an incremental run. In this example, we've made a small change in the small shift register module, and now you see the change in the report. In the image here, we see the small shift register. The status of it is changed to remapped, the reason being design changed, and you can see the timestamp change also. During the incremental implementation, during the reference run, place and route would pack, place and route the design, and then during the incremental run, only the parts of the design that were changed will be worked upon by place and route process, and the rest of the design will be reused. As you can see here, in the incremental run, the primitives that were changed are only being worked upon, which is color coded in the red color, and the green is the one that is reused. In the final stage, place and route will reuse most of the parts of the design, and only the parts of the design that were changed will be worked upon. Now let's look at how to enable incremental implementation. To enable incremental implementation, right-click on the impl_1 directory to set the reference design. You can use the last result as a reference result, or you can use a local result as a reference result if you have already generated a database file previously. In this case, you can have a postSyn file, a postpar file, a postmap file, and a PDC file that can be used as a reference. If users do not select this option after synthesis, full capacity map and par will be executed instead of an incremental implementation. The incremental implementation reports the number of slices that are reused, and the place and route report also shows the number of signals that are reused. As you can see in this example here, the number of slices that are reused are 1008 out of 1012, which is 99% of reused. And in the place and route report also shows that the NBR router has processed incrementally 1008 reused signals, which means about 0.5% of the signals are only reworked upon, and the rest of the signals are reused. More information on how to use the incremental design flow in the beta stage is available in the Radiant help. Now that brings us to the last part of this presentation, where we summarize what we just talked about in this entire presentation. The first thing that I talked about is the virtual I/O flow. The virtual I/O flow helps in streamlining the input and output processors for enhanced efficiency. This increases the productivity by simplifying the I/O management. The block-based design flow facilitates modular design by improving flexibility and scalability of the designs. This helps in enhancing the design flexibility and scalability. The isolation design flow ensures robust isolation for secure and reliable designs, thus improving the security and reliability of the designs. Finally, the incremental design flow allows for more iterative improvements, reducing development time. This speeds up the development with iterative enhancements. From here, our call to action for you guys is please try to explore our tools and discover how these features can enhance your workflow. You can get started today by beginning the use of new features and experience the benefits firsthand. Please also share your feedback, which will help us continue to improve by sharing your experiences in developing our tool flow. For additional information, you can always refer to Radiant Help, which is a comprehensive guide to help users get started with our Radiant tool flow. Along with that, we also have Lattice Insights, which is a training portal that has various courses for users to use and get benefited from. The Lattice Insights can be accessed from www.latticesemi-insights.com. There's also a QR code here which you can scan, which will take you to the same website. That brings us to the last part of this presentation to look at some of the frequently asked questions. The first question is, what are the advantages of using virtual I/O flow? As mentioned, the virtual I/O flow in Radiant is designed to help when your design needs more I/O pins than that are available on the device. This is especially useful for developing intellectual properties or IP modules. The next question is, what are wildcards supported in virtual I/O flow? Yes, wildcards are supported in the virtual I/O flow. More details of this can be found in the Radiant help document. Third question, what are the advantages of using the block-based design flow? Block-based design flow offers several key benefits that significantly enhances the design process for complex projects. This methodology is particularly advantageous for managing large-scale designs and improving overall productivity of providing fast timing closure, design reuse across projects, and enhanced team-based designs. Again, more information about this is available in our Radiant help document. Another question, can a macro created in one device be used for another device? Only logical macros is portable. Firm and hard macros are quite strict and should only be used within the same device because it contains placement and routing information. How can the user know if the isolation design flow is secure? We are working on a flow called the Isolation Design Verification Tool Flow, which can help with this in the future releases, which is currently not available, but you can look forward to this. If my design changes by 20%, can I use incremental design flow to save runtime and guarantee design performance? No. Incremental design flow is more effective for smaller changes, which is approximately 5% of the overall design changes. If users change more than 5%, then it's really going to be really hard for the tool to maintain and guarantee the design performance and also save the runtime. With that, I would like to conclude this session. Please Please feel free to post additional questions and we will get back to you. Thank you for listening.